Alright, so we're deep in the heart of Chapter 6, looking at energy. And we found in last section, our job was going to be to quantify, right? We wanted to measure. Alright, we didn't talk about how we were going to measure it though. So here in Chapter 5, we're going to talk about how we're going to measure it. We're going to use an apparatus called a calorimeter. And the first kind of calorimeter we're going to consider is something that will help us do a constant volume measurement at constant volume. So let's think about what that means. So remember that in order to measure things with respect to a system, right, we could do things in the surroundings. So if we can measure the surroundings, we can indirectly get heat and work measurements with respect to a system, right? So you knew that any heat that was lost from a system was going to go to the surroundings. Any heat that was gained by a system was going to come from the surroundings. Any work that was done by the system is going to go to the surroundings, right? And any work that's done on the system is going to come from or going to be done by the surroundings. So anyways, we've got a really tight link between the system and the surroundings. And what we can't measure with respect to the system, we will measure with the surroundings and then use this important understanding that it's tied to the system. All right, so now we're interested, the way we're going to do this with a calorimeter, calorimeter, we're going to measure heat, okay? And with a calorimeter, we're going to measure heat. We're going to look at a temperature change in the surroundings. And when we see the temperature change in the surroundings, we're going to know that that heat came from the system, right? And the symbol that we're using for heat is Q, right? Remember that? Okay, so interestingly, if we're doing a constant volume calorimetry, then we know that the internal energy, I think it's going to help you if you look at these terms, right? That's the internal energy of a reaction, or the change in internal energy of a reaction, right, is going to equal, what does that symbol mean? Remember, it's the heat, and this means constant volume. It's the heat at constant volume. Now, if you have a constant volume, right, remember W is equal to minus P change in volume. So if the change in volume is 0, then the work is 0, right? And so that goes to 0. That plus 0, therefore the change in internal energy of a reaction is equal, or at constant volume, right, is equal to the heat at constant volume. All right? Okay, so how are we going to keep a constant volume of a reaction? Well, there's a couple ways that we can do that, but one good surefire way is to use a system that does not allow for changes in volume. Okay, so the term that we have for a calorimeter like this is a bomb calorimeter. You know what? I'm really not sure why we call it a bomb calorimeter, except maybe that it could withstand pressure variations like you might see in a bomb. I don't know. And if you don't mind, I don't really care. The point is, with a bomb calorimeter, you have some system. Can you see maybe a big steel cylinder here with a very, very heavy lid, right? This is something that's going to allow for dramatic changes in pressure, and it's not going to change the volume at all. Okay, so in a bomb calorimeter, usually you have water. You have some reaction that's done inside what's the bomb here, right? You have a sample, oxygen, and it's ignited, and so you have combustion, and so you have a change in temperature. You have a change in temperature, and what we're going to do is we're going to simply measure the change in temperature of the calorimeter by using this. Okay, see that? We're going to get the change in temperature of the calorimeter, of the whole calorimeter, like that. All right, so the equation we're going to use for that is going to be, I don't even have it here. The equation we're going to use is going to be the heat is equal to the heat capacity of the calorimeter times the change in temperature. And I de-emphasize this reaction because if you look at this first practice problem that we're given, we could derive it ourselves just by looking at the question. Okay, so let's look at this. When 1.01 gram of sucrose, all right, so we've got the sucrose, which I'm going to write as sucrose because I'm overwhelmed when I see all those atoms there. The mass in grams is equal to 1.010. And look, it's got 4 sig figs. All right, so what I'm going to do, though, is I'm going to get this to moles right away. Before I even look at the rest of it, I'm going to take it to moles. And the formula weight in grams per mole, right? Let's go to a different color for a second. Let's go to black. So that's 12 times 12.01 plus 22 times 1.08 plus 11 times 16.00. And this equals to 144.12 plus, I can't do that in my head. I need a calculator here. All right. 12 times 12.01 plus 22 times 1.08 plus 11 times 16 is equal to 343.88. Equals 343.88. I got tired of doing this here, and I just went ahead. This is grams per mole, right? Because this is the formula weight of sucrose. So it's equal 343.88. Now, if I want moles, then I'm going to do, looks like I'm going to do mass divided by formula weight, right, to get moles here? Okay. So let's do that. What I'm doing right now is I'm taking the mass, 1.010, divided by that 343, and it gives me 2.937. Go back to red now. 2.937 times 10 to the minus 3. I hope you did that also. Okay, so that's how many moles I have of sucrose. And I really haven't even read the question yet, right? All I'm doing is just figuring out how many moles I have. In a bomb calorimeter, the temperature rises. In the bomb calorimeter, the temperature rises from 24.92 to 28.33. 28.33 minus 24.92. 4. I borrowed. That makes that a 7. 3.41. So it looks like the change in temperature, 3.41 degrees Celsius, okay? Find the change in internal energy of the reaction for the combustion of sucrose in kilojoules per mole. So I'm glad we did the moles right there because it's right there. Find the change in internal energy for the combustion. All right, so we know this, that since it's a bomb calorimeter, the change in energy, or the internal energy at constant volume, right, it's bomb calorimeter, is equal to Q at constant volume. Agreed? And Q is equal to the heat capacity of the calorimeter, delta T, right? So, first of all, let's say we know that the heat capacity of the calorimeter, because it's given to us, 4.90, watch this, kilojoules per gram degree centigrade times, and then I've got the DT is right here, 3.14, 41 degrees centigrade. Those cross off. And so the heat that's absorbed by the calorimeter is, just a second, that's 4.90 times 3.41, 16.709. 16.709 kilojoules total, right? That's how much heat was absorbed by the calorimeter. 16.709 kilojoules. Let me make sure, first of all, I got that right. It was 4.9, and 3.41 is, I hope that's right. You know, I'm going to check that before I move on. Just, it's real important that we get that right. 28.33 minus 24.92, 3.4. That's right. Okay. So it looks like this is 16.709 kilojoules, and we want, this is asked, what we're asked for is the heat capacity find this, in kilojoules per mole of sucrose. So we know how many kilojoules are there, right? 16.709 kilojoules. And how many moles of sucrose? 2.937 times 10 to the minus 3 moles of sucrose, okay? So if I just take these two numbers and divide them, I will be done. That'll be in kilojoules per mole of sucrose. All right, so I've got 16.709 divided by 2.937 times 10 to the minus 3. Ought to be a big number, because that's minus 1,000, right? Looks like it's 5.689. 5.689 times 10 to the 3 kilojoules per mole of sucrose. All right. Okay. There's one thing, I'm looking here at my notes, and there's one thing that I see, and that is, this is for the delta H of the delta E of the reaction, the change in internal energy of the reaction. And so one thing I forgot to do was, I forgot to say that QV, looking at my notes here, QV is equal to minus QCal. Why is that? Right? And so that's going to make this a negative, because this was a positive, right? That's going to make this is my QCal, right? My Q of the reaction is going to be minus 16.709 kilojoules. That will make that a minus and that a minus. And the question is, why? Why is this true? Okay? We've said it a couple times in previous videos, but it turns out that's an important point here. If it's multiple choice, oftentimes, you know, it might not be an issue because you'll see it. But if it's not multiple choice, you could get sideways like I did right here in this video.